my talk is focused on some algebraic structures that commonly appear in quantum mechanics. Like you know that there are many mathematical objects, many categories involved in theoretical physics. In particular, in quantum mechanics, the mathematical objects involved, they are more related to functional analysis. And so I'm going to just talk about those structures. I'm going to review some basic notions. I will also present some original results. And the structure of the talk is divided in 3 sections. First, I will present some algebraic structures. Then I will talk about the order topology in order rings and modules. And finally, I will talk about some measures defined on effect algebras and valued on models, on topological models over topological rings. Okay. Well, as you know, the first postulate of quantum mechanics is just a basic postulate. Quantum mechanical system is represented by an infinite dimensional separable complex Hilbert space. This is not really meant to be a physics talk. I'm just going to talk about some mathematical objects related to that appear in quantum mechanics. And some other basic notions. If you have an infinite dimensional separable complex Hilbert space, the observable measurements, they are given by the self-adjoint operators. The unsharp measurements, they are given by the self-adjoint operators, which lie, the positive self-adjoint operators, which lie below the identity. The quantum bits, they are known as the unit vectors, and the quantum states, they are just basically the complex rays. For some other physicists, the quantum bits, they are basically the unit vectors of two-dimensional complex Hilbert space. But for some other, maybe more theoretical physicists, they just consider any unit vector of any infinite dimensional separable complex Hilbert space as a quantum bit. Also, sometimes the unbounded self-adjoint operators, which are commonly defined of a non-closed subspace, usually a dense subspace of the Hilbert space, they are also taken as observable measurements. But here we will only stick to the algebra of bounded operators. Okay. Well, and also, as you know, the generalizations of the previous settings, basically the typical generalizations, B of H, that is commonly generalized as a non-commutative unital C-star algebra. A of H, the real vector space of self-adjoint elements, that's generalized as the self-adjoint elements of the C-star algebra. And this is something curious in the theory. The subset of positive self-adjoint elements which lie below the identity, this is generalized as an effect algebra. I'm gonna review now the notion of effect algebra. It's not generalized as a subset, or I mean, according to the first 2 items, the natural generalization should be the positive self-adjoint elements of the C-star algebra, which are less than or equal the unity. But for some reason, in the literature, the positive self-adjoint elements lying below the identity, the unsharp measurements, also called effects, they were generalized as an effect algebra, which is some type of universal algebra. I will later talk about the relationship between effect algebras and C-star algebras. Well, the definition of effect algebra is relatively recent, from 1994. It's just basically a universal algebra. It's a set endowed with the partially defined binary operation, a unary internal operation, which is the complementation, or orthocomplementation, and two nullary internal operations, which are 0 and 1, satisfying the following conditions. It's basically the natural conditions: commutativity, associativity, orthocomplementation, and 0-1 law. The definition of effect algebra comes from the theory of come from positive self-adjoint operators that lie below the identity, but it really is not only a generalization of those measurements, but also a natural generalization of Boolean, of abstract Boolean algebras. And this is why measures defined on effect algebras were also considered, because you can easily prove that every Boolean algebra is an effect algebra, but not the other way around. Like, not every effect algebra is Boolean algebra. So those categories, they are not isomorphic. Well, like I was mentioned before, I'm still reviewing some basic notions of quantum mechanics. If you have an infinite dimensional separable complex Hilbert space, then the subset of positive self-adjoint operators which lie below the identity with that partially defined binary internal operation, that's an effect algebra. That's actually the first example of effect algebra in the literature. But you can actually take it further. The authors that defined effect algebras, they didn't do it in the paper, maybe because they avoided C-star algebras, I guess, because they were more interested in a proper structure that contains the effects. But you can easily prove that if it's actually essentially the same proof as the example above. If it's a C-star algebra, a unital C-star algebra, then the positive self-adjoint elements which are less than or equal to the unity is an effect algebra with the same partially defined binary internal operation. So you have the basic objects that appear in quantum mechanics, they can be generalized on one side with C-star algebras, and on the other side with effect algebras, because every C-star algebra contains an effect algebra, but there are other effect algebras which are not which cannot be embedded into a C-star algebra. So from this starting point, so we were wondering about different generalizations of operator theory, of the algebra of operators on a Hilbert space or on a Banach space. It depends, on what you want to generalize. So the first step that we took was the spectral decomposition. There's the typical spectral decomposition theorem. And that can actually be easily taken to an abstract unitary algebra over a field K. This is purely algebraic. No topology is needed for this. So, well, the spectrum of an element, the definition of the spectrum is already known. It's just the same definition as in the classical theory. The decompositions of the spectrum, if you take a Hilbert space or even in a Banach space, it also works. You can prove that if you take the algebra of bounded operators on a Banach space, then the point spectrum, the continuous spectrum, and the residual spectrum, they verify those conditions there. Here, the point spectrum is just basically the eigenvalues. It's just all elements in the field. Okay. Let me here maybe algebraists don't like what I'm gonna say now, but for us a field is a commutative division ring. Okay, in the non-commutative case we will speak about division rings. Okay, but field means commutative because for algebra, in order to be able to the scalar elements of the field, in order to be able to move them around the elements of the algebra, you need commutativity. This notation, this means the left divisors of 0. So the eigenvalues, they're just basically all elements in the field, so that this element of the algebra is a left divisor of 0. Obviously, if a left divisor cannot be an invertible. The continuous spectrum is just all scalars, so that this element of the algebra is not a left divisor or a right divisor or an invertible, obviously. The residual spectrum is just all scalar, so that this element of the algebra is a right divisor but not a left divisor. So you can actually these three sets hold for the algebra of bounded operators. So this is the natural generalization. Then you obviously get the decomposition theorem. This is just a trivial theorem with these previous definitions. So the key point is to prove that these definitions are preserved when you go down to the algebra of bounded operators. So then there's also the approximated spectrum, the approximated eigenvalues, and for that this is not purely algebraic. Here you need some topology. This is completely purely algebraic, but here you need some topology in order to define the approximated spectrum. So then you need the definition of a topological divisor, which includes the typical definition of zero topological divisor, which is just basically R is a topological divisor of S if there exists a subset so that its closure that does not contain 0 and S belongs to the closure of R times T, and the set of topological left divisors is denoted as TLD, and the mirror definition applies for the set of topological right divisors. And then you can easily prove if you define the approximated spectrum in a topological unitary algebra, you define it as all scalars, so that A minus lambda 1 is not is a topological left divisor that also holds for the algebra of bounded operators on a Banach space. Okay, so following this trend, we were wondering, so that there is a very well-known result in C-star algebras, which says that the boundary of the invertibles in a C-star algebra, in a unital C-star algebra, well, actually it holds in a Banach algebra, in a unital Banach algebra. The boundary of the invertibles, they approach it is contained in the set of topological divisors, left and right. So we wanted to generalize that for not only for general norm algebras, but also for norm rings. Actually, it can even be generalized to semi-norm rings. So then, but we had to use not only the invertibles, but the absolute invertibles, which are the elements of which are the invertibles of the ring, which verifying that condition. You know that for absolutely valued rings, you know the absolute value in a ring. Here, all rings are going to be associative. Okay. So if you take an absolute value in a ring is multiplicative. It verifies, as you know, this condition. But in a norm in a ring is not multiplicative. It is sub-multiplicative. So then you have this inequality. So this equality already provides you, already gives you that all invertibles satisfy easily this condition, you know. But here, since you have an inequality, then you don't have this condition, you know. The condition that you have, as you know, the unity is always, the norm of the unity is always greater than or equal to 1. And even if the ring is unital or the algebra is unital, that means that the unity has norm 1. You still you cannot still accomplish this. So this is basically, you know. So eventually, what you get is that this is greater than or equal. So you have an inequality. So for those invertibles that satisfying the equality, we can accomplish the following theorem. If you have a non-zero element, this works for the topological divisors of non-zero elements. For you have the topological divisors of a zero element, then you cannot have closure there, but the boundary. That's the classical theorem in C-star or in Banach algebras. So the closure of S times the subgroup of absolutely invertible elements minus 0 is contained in the set of topological left divisors. Well, you can actually prove that the subset of absolute invertibles is a subgroup. Actually, they can be easily characterized. So a norm ring, the subset of absolute invertibles is, or the subgroup is non-empty if I don't leave. The norm ring is unital, means that the norm of the unity is equal to 1, and actually 1 is would be an element, an absolutely invertible. Well, so we kept maybe the below theorem should go first. I'm going to talk about this theorem now. You can actually prove if H is a complex. Well, it also works for real Hilbert spaces, and you know that the surjective linear isometries, they can be easily characterized as the unitary operators. Okay, that's a classical result, but actually surjective linear isometries on a Hilbert space, they are exactly the absolutely invertibles of the Hilbert space. So then we managed to prove that the group of surjective linear isometry is not a normal subgroup of the group of isomorphisms on H. So essentially, this is just basically saying that the absolutely invertibles of this algebra, this is not normal, not a normal subgroup of the invertibles of this algebra. Again, this is this subgroup. This is exactly the unitary operators and also the absolute invertibles, and this is just the isomorphisms. So now we are working on somehow transporting the second result to the scope of general algebras, general norm algebras. Also, the first theorem we were just because you know that normal subgroup that involves somehow like a conjugation condition related to commutativity. Actually, in commutativity, everything is a normal subgroup. Working on that, we managed to prove that if X is a Hausdorff locally convex topological vector space, real or complex, then if an operator commutes with all rank 1 projections, then it's a multiple of the identity, which is this is a classical result in vectors in linear algebra, vector space theory.
What do you mean by rank 1 projection? How do they look like in your
This is if you have a locally convex space, it's just a map which is an idempotent for the and the rank. The map is defined. Okay, so you can fix x0 in X and x0 in the dual, and this is because the key point here is that the space is Hausdorff and locally convex, because otherwise, if it is not Hausdorff or if it's not locally convex, it's hard to say, because not Hausdorff, non-locally convex topological vector spaces are extremely hard to manage. But definitely, if you drop the Hausdorff hypothesis, then you find a lot of pathological phenomena. So in particular, you don't have the Hahn-Banach extension theorem. So because of the Hausdorff locally convex, you have the Hahn-Banach extension theorem, and then you can prove that for every non-zero x, there exists an element in the dual, so that this is different from, well, actually equal to 1. Well, you can just make it equal to 1. So you can define the projection as x0, y, x0 is just a projection of rank 1. And so this is a classical result. It is a classical result that if an operator commutes with all, if an operator commutes with all operators, then it's a multiple of the identity, and we managed to prove it for Hausdorff locally convex topological vector spaces, and it is not necessary to commute with all operators, but only with the rank 1 projections. And now our efforts are focused on providing a similar result for unitary algebras, because in an algebra you can actually easily take an idempotent element. Actually, in if it's a C-star algebra, then the orthogonal projections can actually be characterized as all projections, which are self-adjoining, and then automatically they become positive. And so then we believe it is interesting for a non-commutative C-star algebra to prove to generalize both results. If an element commutes with all orthogonal projections, I mean all elements satisfying these two conditions, then it should be a multiple of the identity, and also the below result. If you have in a C-star algebra the unitary elements, which are the invertibles, so that the adjoint is exactly the invertible of the element. If this is a normal subgroup or not, the expectable theorem should be that it's not a normal subgroup of the invertibles. Obviously, this is for unital non-commutative C-star algebras. So we are focused on right now on transporting those two theorems to abstract algebras, or at least abstract C-star algebras. Well, how much time is left? 3 minutes. Okay. And I'm gonna just review quickly. This is just basic notation of partially ordered sets, the typical intervals. In totally ordered sets, the notation interval is used, but in partially ordered sets, it is also used, the interval notation, but also this notation which is typical from filters and Bornologies. Well, the ordered topology, this is a very well-known result. You have a poset, a partial ordered set, and the set of unbounded intervals is a subbase for a topology on X, if and only if for every X either one of these two sets is not empty. And then for order rings and modules, you can provide sufficient conditions for the order topology to become a ring or a module topology. Well, you know, an order ring is just a ring endowed with a partial order satisfying the typical, compatible with operations. And a very well-known fact is that in an order ring, if 0 and 1 are comparable, then 1 has to be necessarily still greater than 0. Okay, we're assuming that the ring is not the trivial ring, the 0 ring. And the characteristic of the ring, it has to be 0, and actually conversely, every ring of characteristic 0 can be endowed with a maximal unital ordering. It is hard to endow a ring with a total order. That's very hard. But endowing a ring with a partial order is very easy. Actually, it can be done in any ring of characteristic 0. And the same for a module, you know, like an ordered module is an order compatible with operations, and it's the same. If a module is, if you have a module of a unital ordering, it can be done with a maximal ordering. As a typical example, the real vector space of self-adjoint elements, that's a partially ordered vector space over the reals, you know, a module over the reals. With endowing the reals with the usual order. The typical theorem, the first example of C-star of effect algebra seen in a C-star algebra, it can be easily generalized to order modules over unital order rings. If you take an element that is still greater than 0, then that's easily acquires a structure of an effect algebra. That's why it is very interesting to define measures on order modules over order rings. Well, the topology, in order to define measures on order modules or rings, the right topology to work with is the order topology. Is the topology given by the subbase described by the unbounded intervals, but it's not always a topology. But even if it is a topology, it's not always a ring topology or a module topology. But the order topology, at least, is a well-defined topology if and only if there exists at least one element still greater than 0. In particular, if the ordering is unital, means that 1 and 0 are comparable, then 1 belongs to that set. So then that set would be different from not empty, and therefore the order topology is at least a topology. And finally, if a unital order ring, if R is a unital order ring, and the set of stilly positive elements is downward directed, and 0 belongs, so then the order topology is a topology. So then you can take the closure of the stilly positive elements. If 0 belongs to the closure of the positive elements, then the order topology is an additive ring topology. You can accomplish that. This is like one of our most recent results, and actually you can adding an extra condition which is somehow artificial, and that's why I didn't type it up here. But adding an extra condition, then you can accomplish that the order topology is a multiplicative ring topology. Just to finish, this is not a characterization of ring topology for the order topology. You can easily construct order topologies which are ring topologies and are not, and they do not necessarily satisfy these two conditions. So there is not a characterization, but at least it's a sufficient condition for the topology to become a ring topology. And then you can define measures on which are defined on effect algebras and take values on an order ring or module. Sorry about the time, but I should stop here, right? Okay. Yeah. Okay, thank you very much.